So welcome to the lecture. We will continue our discussion about tensors. Before that, let's start with some brief recap. So we introduced the notion of a PQ rank tensor, which is defined as a multilinear map from P number of one form and Q number of vectors to a real number. So you can think this is like a slot machine where the first P number of slot you can put some one forms, and in the next Q number of slot you can put some vectors, and it will give you a real number. And in the coordinate basis, you can represent this PQ rank tensor by a component and a basis of this form. So you can see that in the component there are P number of upper indices and Q number of lower indices. Remember, each of these news and news takes 4 values 0, 1, 2, 3, and the basis is formed by taking tensor product of dels and coordinate differentials. Basically, you are taking tensor product of various vector spaces and creating a larger dimensional vector space. And the PQ rank tensor is the element of this larger dimensional vector space. And remember, this del mu is a shortened notation of this, just to remind you. And also, this is the defining relation between the basis of a one form and a basis of a vector. Basically, dx takes a del and spits out Kronecker delta. Remember, when mu equal to mu, this is 1, or when mu and mu are not equal to each other, this is 0. That is the definition of Kronecker delta. Okay. Then we discuss something called the index contraction. So, for example, let's take an one form omega, and it acts on a vector v, and we can show that this gives this in terms of the component. Remember, and you notice carefully that this index mu is repeated, and repeated indexes are summed over, and we call this mu index or contracted index. Okay. So remember that if two indexes are contracted, one must be in up index and one must be a down index. So you have to be careful about the position of the index. And naturally, we check that this remains invariant under Lorentz transformation. So it's actually forms a scalar, basically a 0, 0 rank. So you can generalize this argument for product of arbitrary number of tensors. So let's take the component of 3 tensor A, B, C, and we can write down this particular product where you can see that mu and nu indices are contracted. Only lambda and kappa indices are free, and you can check that this is a component of a 0, 2 rank tensor. So to check how these things transforms under a Lorentz transformation, you just have to use that a fact that A mu nu will transform under some inverse Lorentz transformation, B and C will transform some Lorentz transformation, and so on. Okay, so please do this exercise. So the lesson that we learn from this is that if we are given some product of this kind, the combined object will transform accordingly the number of the free indices. That means the rank of that object will be determined by how many number of the free indices are there. So in this case, there are 2 free indices, which is written downstairs. So we can see that naturally this transforms as a 0, 2 rank answer. So of course, for this example, if all the indices are contracted, this will be a scalar. It will remain invariant under Lorentz transformation. But in general, a PQ rank tensor, the component of that will transform under Lorentz transformation. For example, if you go to a coordinate system x to x prime, so the component in the prime will related to the component in the unprimed coordinate system by this. So all the upper indices will transform accordingly by the element of the Lorentz transformations, and the lower indices will transform accordingly using the elements of this inverse Lorentz transformation that we have discussed in the previous lecture. So then we asked that, are there any more non-trivial tensors which are not of 0,0 rank, which remain invariant under the Lorentz transformation? And we find three such examples which we call invariant tensor. The first one is the Kronecker delta, which is written in the coordinate basis like this way. This is a 1,1 rank tensor, and of course this is the component which we denoted by delta with one index up and one index down. When mu and nu are same, it is 1, and when mu not equal to mu, it is 0. And also we have identified the Minkowski metric tensor, which is a 0,2 rank tensor, also invariant under Lorentz transform. In fact, the definition of the Lorentz transformation, the Lorentz group, is that it preserves the Minkowski metric. And then we have introduced one more tensor, which is known as the Levi beta. It's a 0,4 rank tensor, and it is totally antisymmetric in these four indices, mu, nu, rho, sigma. And we have fixed the convention such that epsilon 0, 1, 2, 3 is 1. And if you do any cyclic permutation of these indices, it will be +1, and any anticyclic permutation will give -1. And if any two indices takes the same value, it will be 0 because it's totally anticyclic. And one can show that it remains invariant only under proper Lorentz transform. And we leave that as an exercise for you. Okay, so now let us proceed to discuss some more new things. First, we will discuss mapping of a vector to one form. With the help of this Minkowski metric. So we know that eta is a 0,2 rank tensor. Also, it is symmetric. That means that if we supply it with the two vector, let's say v and w, first of all, it will give us a real number. Also, it is same as if we interchange the position of w and v. So this gives that it's a symmetric. Now, of course, this gives you a scalar, but let us ask the following question. Suppose we have eta and we supplied it with only one vector. Then what is this object resulting? It doesn't matter which slot we put v because it's a symmetry. Yes. So let's proceed from here. So let's write eta in terms of the component and basis. So eta mu nu lab dx mu tensor product dx mu, and we have inserted one vector in the first slot. We'll have this. So now let us write this v itself in terms of component and basis. V lambda lambda. Remember that these are all linear map. This is just a number, it will come out. Okay. Eta now we know that this will give a Kronecker delta. So we get the following. mu nu p lambda. Then let's write this again. This is Kronecker delta. Then you have dx. So we have dropped this tensor product notation because this is just some scalar number, and multiplication with a scalar with a vector can be done using ordinary multiplication. No need of this ordered product. So mu nu and remember the right hand side is nothing but this. And because this is a Kronecker delta, so we have to set mu equal to lambda. Otherwise, this is just 0. So then we have beta mu dx. So now you can see that what is this? This is nothing but a one form, right? Because this is the component of that one form, and this is the basis. So we call this as a one form which is dual to the vector v mu. We have this vector v mu del mu, and there is a dual one form we will use the same symbol for the component, but the index down. Right? V nu dx mu, or v nu is nothing but eta mu v nu. So metric serves as isomorphism between the elements of the tangent space to that of a elements of a cotangent space or the dual space. Provide the isomorphism. And this is we called the lowering of indices. So what it means is that if you contract a vector with eta in this suitable way, then you can lower the indices and get a corresponding one form. So you can generalize it for arbitrary ranked tensor. So let's take an arbitrary ranked tensor which have some index and there is some new here, and then it will have some lower index also, ionic rank. Now back with eta mu nu, then you will get anything, but this mu will now go downward corresponding position. This is how we will lower the index using the Minkowski metric tensor. Of course, this we will generalize later on for arbitrary metric tensor, but we will postpone that discussion for the later half of this course. After this, let us discuss inner product of two vectors. So let's consider two vector v and w. So their inner product is defined as v and theta. So when we are denoting the inner product of 2, 4 vector, we are denoting the dot in the down. Compared to the dot product that you are familiar with from your calculus or vector analysis in R3, where you have 2 Euclidean vectors. So dot product you denote by the same symbol but middle of. Just keep in mind the difference between these two conventions. Okay, so let's see what happens in terms of component basis form. So we know that theta again dx mu dx mu. In the first slot you have v, and the second slot you have w. And we just argued that theta is a symmetric, so it doesn't matter which slot we put v and which slot we put. We can interchange the same result. Now writing this v and w itself using a component and basis alpha. Now again, these are linear maps, and this is a number. It will go out. F mu. Theta w. So this is also a number. I'm just taking it out and write it in before. Also, we have dropped this tensor product notation because it's just a scalar number, and we know that this gives Kronecker delta alpha. Okay, and let's simplify this. Yeah, VW, then theta mu. We have to set mu and alpha same and mu and beta same. So to do that, yeah. So this is how you get in our product of 2 vector with the help of the Minkowski metric. So remember that eta 0, 0 is -1, and eta 1, 1, eta 2, 2, and eta 3, 3 are 1, and rest are 0. And let's write this sum explicitly by decomposing it into a 0 and the spatial part. So we'll have sum is that P0 W0 times eta 0, 0, which is -1, and the rest of the terms are P1 W1 V2 W2 P3 W3. Then we can see that this is nothing but P0 W0 plus this part is nothing but the usual dot product that you encountered while doing stuff with the 3 vectors. You just type them as the arrow. Now this dot is in the middle just to make it different from this dot, and this is the 3 vector. Also, using this index lowering technique, we can rewrite this in the following way. V dot W theta mu V mu W mu. But if you look at it, this is nothing but V nu by this index lowering technique. So you can write it mu W mu. Now this makes sense because at the end of the day, this should form a scalar. So all the Lorentz indices are contracted. Each are the upper index and the lower index, and they are contracted. They are same, which means it's a sum of them. It makes sense. And analogously, you can also see from here that eta mu nu, w nu is nothing but some w mu. So you can also rewrite this as g mu w. Again, the Lorentz indices are contracted, forms a scalar, and this is same as this. You can check it by writing component by component. So if you go to a prime frame, so it will obviously in same. So invariant under Lorentz transform. Of course, where v prime and w prime are the components of this individual vector at the prime frame, but the inner product of these four vectors remains invariant. Lorentz transform. Now, this gives us a way to define the so-called norm of a vector, or rather squared norm. So how do we define? So squared norm of a vector, nothing but v dotted with itself. Okay. Remember, these are four vectors. Oh, so, and we will also refer to this for simplicity, just v square, dropping this. So this is. So now we know that this theta has an indefinite signature. That is one of its eigenvalues is minus negative, other three is positive. So we know that this can be positive, negative, or not. So when this is greater than 0, known as space-like. When this is less than 0, call it a time-like vector. And when this is 0, we call the null. Like vector. Okay. So let's take some example of this thing. So let's first consider the force velocity of a point particle moving on some trajectory with some velocity, free velocity, vr. What is that? So mu is the force velocity of a point particle. We have zeroth component is just gamma times c. Gamma is the Lorentz factor, and the spatial components are nothing but this is the free velocity. Is the component of force velocity. Free velocity. And gamma, let's write it once more, 1 minus p square plus c square by c square minus the Lorentz factor. Now you can define the corresponding one form by using the lowering of index technique with the help of the Minkowski metric. which is eta mu nu, and you will get the following C and 1. Because if you look at the sum carefully, so the 0 component, which will be equal to 0, which is 0, so this must be 0. So eta 0 0 times u 0, which is gamma c, but eta 0 0 is minus 1. So when we raise lower the indices with the eta, you will see that there will be a sign change in front of the 0th component. And of course, because eta 1 1, eta 2 2, eta 3 3, it's all plus 1, so there is no. And then what we can calculate the squared norm, which is this. It is nothing but u dot u, and in component notation this, and this will give you fact or that. If you write it explicitly, this is like u0 then times u0 up plus u1 down times u1 up, and so on. Just do that simple algebra. You get the following. Now we know that this v is always less than c. Nothing can propagate faster than the light. Especially a point particle of mass m will always propagate. Will have a 3 velocity, and magnitude of that will be always less than the speed of light. So v square by c square is always less than 1. So this is a positive number, hence this is less than v. So this is a timeline vector. And this is we know from our elementary special rate. Similarly, you can check that for momentum, it's denoted by small p, the 4 momentum of a point particle of waves, whatever one, the 0th component is E by C. Let's start the 3 momentum associated with the 3 velocity part. And for this point particle, as usual, you can write E equal to m times u. So E square equal to m square u square. And hence, what should we get? Remember, u square is m square gamma square c square 1 minus c square by c square. But this is nothing but 1 by gamma square and m square. So if you go back, and also you can write it here, minus c square, using the fact that again this is 1 over gamma square, and so. So we will see that in natural unit, we set c equal to 1. That means you are making the dimension of time and the space equal. And in this unit, you can see that both u square is -1 and p square equal to. And again, this is a timeline. So also try to write down the 4 vector associated with the propagation of the wave and check what it is. So for example, so you can write your wave vector as omega by c. Sorry. These the three spatial part associated with the spatial coordinate omega, the angular frequencies, and for a photon or light wave, this must be 0. You will see that this implies that omega equal to c times mod of k. So you can write here the 4 wave vector as mod of k and there will be many more examples that we will encounter later on of time-like, space-like, and the null vector. So let us make one comment. Remember that Minkowski metric, the indefinite signature, it's -1 and then +1 +1 +1, right? But still it does not lead to any inconsistency. We can meaningfully define this time-like, space-like, and null vector. So norm of the vector can be negative, positive, or 0. And we don't run into any inconsistency because there is no degeneration. We can invert eta. Inverse exists, right? Eta inverse. In fact, it is same as eta. So for Euclidean kind of metric, where you have or plus, let's define the Euclidean metric by some g, and you take to vector in U, calculate its norm. So in general, it is greater than 0. When this is 0, it implies U has to be. It's an if and only if condition. Now we have for Lorentzian metric, for example, Minkowski or any general Lorentzian metric with an indefinite signature, we have to change this degeneracy condition. So if we have given a Lorentzian metric, we just symbolically define eta, take vector u and take another vector v such that this is 0 for a given vector u, and for all, this is important, for all choice of v, then only it will imply that u is 0. So in this way, we are making sure that there is no 0 eigenvalue of the metric, and you can invert it easily, and you don't run into any problem. So you can, although it is indefinite in signature, we can easily define time-like, space-like, or null vectors, but it does not possess any 0 eigenvalue. So we will end here. Thank you for listening.